Now let's look at another proposition. We will use the lemma we just introduced in the previous video to prove this proposition. It says let x naught be any non-zero point in the domain of convergence of this power series. Okay, we let r be a number greater than 0 but less than the absolute value of x naught. Then the closed interval from negative r to r must be in the domain of the convergence of the power series. And this interval is also in the domain of the convergence of power series of the power series, which is the summation k from 1 to infinity k times c sub k times x minus 1, x to the k minus 1, which is actually the derivative for each term of this one, right? We take the derivative. So the first term, there is no 0, right? Like when k equals 0, take the derivative would be 0. So there is no 0, k equals 0 anymore. So here k is from 1 to infinity. And moreover, both power series converge uniformly on this closed interval. So this proposition tells you the construction of the convergence and the domain of the convergence. It's kind of symmetric. Okay. You will not have it's impossible if you the domain of the convergence it's kind of symmetric. Okay, it's kind of symmetric. There is a middle point on it. Okay, it's impossible that a 0 is here. Okay, it's impossible that this 0 is here. Otherwise, you cannot find this r. Okay, you will not have this result, right? This result tells you that the 0 of the domain of the convergence must be in the middle. Okay, so this proposition just tells you the constructions of the domain of convergence. So now let's look at the proof. This is proof a little bit long. Okay. So let's start from the beginning. Let's prove the original, the first power series, the original power series, which is convergent on this interval, and moreover, it's uniformly convergent. So now we take arbitrary x in this interval. Okay, then we prove that the power series at this x is convergent. So since it's arbitrary, so its converges on this interval. Okay, and we also let x is not 0. If x is 0, it's always convergent, right? It's a finite number. So if x is in this interval, so we have this result, right? And the absolute x should be less than r, greater than 0. Since it's not equal to 0, so it's greater than 0. And r is less than x naught, the absolute value of x naught, right? This is the construction, how we choose r and how we choose x naught in the proposition. So since this one, x naught is in the domain of the convergence, so this series converges, right? The power series converge at x naught. So the convergence at x naught, so there exists number m, right, constant m greater than 0, such that each term is bounded by this m, right? Because if it's convergent, so each term, when k approaches infinity, this term would be approaches 0, will approach 0. So of course, every term is bound. You can find it must be bounded, right? It must be bounded. So it's bounded by this capital N for all k. So now let's let alpha be r over the absolute value of x naught. So r and x naught are given. So alpha is less than 1, right? Greater than 0. So now let's look at the general term for the power series. Okay, the power series at x, this is the general term, right? We can write this one as this one, right? We multiply the x naught to the k and divide by x naught to the k, right? And and this term x over x naught, of course, is less than r over x naught, right? Because of this inequality. So x over x naught is less than r over x naught, right? So it's less than equal to m times alpha to the k. So we denote this inequality by star. So now we want to show that this series, okay, this series is convergent. Of course, you can use the geometric series, right? This is m times this result, which is if you take m out and the series becomes a geometric series, right? It's equal to 1 over 1 minus alpha is less than infinity. So this one, by this inequality, you have this one less than equal to this one. And this is finite, this series is finite, so this is finite, right? This is the absolute convergence, right? So of course it's convergent at this x. So since x is arbitrary, so this power series converges on the whole interval from negative r to r. Okay, then we can have by the lemma. Okay, the lemma says, and this, if you have this inequality, each term is bounded by some constant times some constant alpha raised to the power k, then this power series is uniformly convergent, right? So of course it's uniformly, it satisfies the condition of that lemma. So it's uniformly convergent. So this is just for the part of the original series. So the next series is the derivative, the series of the derivative for each term of the original series. So now let's look at the proof for the other one. We still give the same setups. Okay, we still have the same setup for the x and the x not 0 and have this inequalities. Then let's look at this term. This is the general term, right? K plus 1 times c sub k plus 1 x to the k's power. Okay, do the same tricks. We multiply by r to the k and divide by r to the k, right? It will not change anything. And we change here for the power r to the k plus 1, right? To have the same index here. So we need to divide by r, and this is positive, so we can take out the absolute value sign. And we know by the first part, the proof of the first part, okay, we know that this one is bounded by m times alpha to the k. So here alpha is x naught over r. Okay, and of course alpha is greater than this one. So we can replace here by alpha also. So alpha squared to the k's power, right? So we let, for our convenience, we let beta to be alpha squared, which is alpha is less than 1. So alpha squared is also less than 1. All right, so beta is less than 1. So we can write this one as k plus 1 over r times m times beta to the k. So now we rewrite this one. We want to show that the power series for the series for this part, which is convergent. If this is convergent, then the series of this one is convergent, right? So we note that this series, right, which is k plus 1 times beta to the k's power, converges. We can use the ratio test. You can do it by yourself. It's very simple, easy. And then this is our aim, right? This is the derivative for the original series, power series for each term. Okay, so this is the series. It's equal to, so we want to write k from 0 to infinity. So here is k from 1. So let's shift a little bit. Okay, shift by 1 unit. So it becomes the same thing, right? So here, this is the general term of this one, right? So this one is bounded by this inequalities, which is bounded by this one, right? Bounded by this one. By this series, and this series we just show that this is m over r is a constant you can take out. Then you have this one, right? And this series we just show that it's convergent. Okay, it's convergent. So this is the convergent. The bigger one is convergent. The smaller one must be convergent, right? So the convergent at this x. So since x is arbitrary, so it will converge on this whole interval. Okay, so the next thing is we want to show that it's uniformly convergent. But here is the uniformly convergent, we should have some inequalities that here should be some constant times some constant which is less than 1 raised to the power k, right? This is by the lemma. We can use the lemma to prove that. But here we still have some k. So we want to do a little bit of change. So we let beta prime, which is beta is less than 1, so we can always find this beta prime, right? So the beta prime is between beta and 1. So the beta over beta prime would be also less than 1. And we form a new series, this series, okay, the series converges. You can use the you can treat this one as a new constant which is less than 1 by the ratio test. Okay, it's very direct work. You can do it by yourself. It's by the ratio test. It's convergent. So it's convergent. That means the term is bounded, right? Each term is bounded. So so there exists a constant c such that this one is the general term is bounded by c for any k. Okay, for any k, so we have so we can multiply beta prime to the k's power on both sides, right? You will have this one because it's positive, right? It's greater than 0. So you have this one. So we replace in that series, okay? In here, okay, in this inequalities, we replace this one by c times beta prime to the k. So you will have this inequality. Okay, so m over r times c, these are constants, right? This is constant times some constant which is less than 1 raised to the power k. So this satisfies the conditions of the lemma. So we can use that lemma. This one is equal to this series converges uniformly on the R. Okay. So now let's look at the last thing for this section. That we let D be the domain of convergence, right? And we let R be the supremum of the absolute value of x, where x is in the domain D. Then you can show that, okay, this is you can use this one as a practice. You can show that the closed interval from negative R to R is D is a subset of the closed interval from negative R to R, which D also contains the open interval from negative R to R. So you can see the construction for this D, except on the end points, it should be symmetric, right, about the origin. So this R is called the radius of convergence of the power series. Okay, so that is the end of this section.